Welcome to this explainer. We often picture chemistry as just a bunch of static letters and lines on a page, but honestly, the reality is a constant, highly dramatic quest for structural peace and stability. I'm absolutely thrilled to have you here today as we journey into the invisible world of microscopic molecules.
So, let's dive right in with a simple question. What does a molecule actually do when it's under way too much stress? I mean, just like us, when molecules get forced into these uncomfortable, high-energy situations, they desperately want to find a way to relax. Today, we're going to look at the fascinating, almost unbelievable ways molecules will actually tear apart their own skeletons just to find a little bit of relief.
Here is our roadmap for today. 1. The unstable carbocation. 2. Paths to chemical stability. 3. The art of rearrangement. 4. Mapping the energy shift. 5. Wagner-Merwin rearrangements. And finally, 6. Relieving molecular strain.
Section 1. The unstable carbocation. So, what is a carbocation? Well, it's an intermediate species, meaning it's really just a fleeting, temporary phase in a chemical reaction. It features a carbon atom bearing a positive charge, and because it's literally missing its ideal number of electrons, it acts as a Lewis acid. Simply put, it is highly reactive, incredibly awkward, and desperately seeking electrons to achieve a comfortable, stable state. It absolutely cannot stay the way it is.
Moving on to Section 2. Paths to chemical stability.
Okay, so our stressed out carbocation basically has 4 main avenues to find some chemical peace. First, it can react directly with a nucleophile, an electron-rich species. Second, it could lose a proton from an adjacent position to form a stable alkene double bond. Third, it can add to an unsaturated compound. Or fourth, and this is where things get truly mind-bending, it can rearrange its own internal structure entirely.
Check this out. We've got a highly stressed tert-butyl carbocation here. To neutralize that glaring positive charge, it reacts super fast with a chloride ion, which is our nucleophile. In this quick Lewis acid-base reaction, it just grabs those available electrons, neutralizes the charge, and boom, forms butyl chloride. Problem solved, stability achieved. But what happens when there isn't an easy electron donor around?
That brings us to Section 3, the art of rearrangement.
Think of this kind of like rearranging heavy furniture in a really cramped room. On the left side, we're looking at a primary carbocation. It's super awkward and highly unstable because that positive charge is stuck right on the end of the chain. To fix this, an adjacent alkyl group, or maybe a hydrogen atom, literally picks up its electrons and just shifts over one position. We call these 1,2-alkyl and 1,2-hydride shifts. By shoving this furniture around, the molecule transforms that awkward primary state into a secondary or even better, a highly secure tertiary carbocation.
All right, Section 4, mapping the energy shift.
So, the why of all this is perfectly shown right here on this topographical energy map. Our vertical axis represents energy, which basically translates to stress. We start on the left, but I really want you to focus on the valleys. Valley B is our initial classical carbocation. Notice how high up it is? That means tons of internal energy and stress. Now, look over at Valley D. That is our rearranged carbocation. It is so much lower on the energy coordinate. The molecule is more than happy to push through that transition state at peak C, just sliding that migrating group across to a new orbital because that final destination in Valley D offers massive energetic relief. It's simply seeking the lowest possible energy state.
Next up, Section 5, Wagner-Merwin rearrangements.
Originally discovered when scientists were looking at alcohols under acidic conditions, a Wagner-Merwin rearrangement is a very specific type of structural shift. It's entirely driven by the molecule's intense desire to do 2 things: form a more stable carbocation, like we just talked about, and reduce steric crowding. Basically, it just wants to give its bulky atoms a little more physical room to breathe.
Let's actually walk through the classic example of this, the rearrangement of neopentyl alcohol into tert amyl chloride. Step 1. In an acidic environment, the alcohol's oxygen gets protonated. Step 2, it drops a water molecule, and that leaves behind this highly unstable primary carbocation. It's trapped, it's stressed out. So step 3 kicks in. A methyl group from the carbon next door pulls a 1,2 shift, bringing its electrons along to create a much more stable tertiary carbocation. Finally, step 4, a chloride nucleophile swoops in to lock down this new highly stable structure. The molecule literally rewrote its own skeleton just to survive the reaction.
And, here is why this actually matters to you and me outside the lab. This exact microscopic quest for stability literally powers our world. Acid-catalyzed isomerizations rely on these carbocation rearrangements to create highly branched-chain alkenes. And that process is heavily used in petroleum reforming. So yeah, we literally harness this invisible molecular stress to create better, way more efficient fuels for our cars. How cool is that?
Okay, moving to our final section, Section 6, relieving molecular strain. Let's contrast electronic and geometric stability for a second. We've talked a ton about electronic stability, shifting from a primary to a tertiary carbocation. But sometimes a molecule is actually struggling with geometric stability. Imagine a tiny four-membered carbon ring. The angles are forced tightly together, causing intense angle and torsional strain. Honestly, it's exactly like having to wear a belt 3 notches too tight after a massive meal. The molecule just desperately needs to let the belt out.
And that brings us to the Tiffano-Dumjonoff rearrangement. This is a brilliant molecular shift where that cramped, highly stressed ring literally just pops open and expands. By shifting a methylene group over to a developing primary carbocation, the molecule actually sacrifices a little bit of electronic stability at first, but it does this to drastically decrease its angle strain. It transforms a tiny, cramped ring into a larger, roomier homologue. It's sort of like moving out of a tiny studio apartment into a spacious one-bedroom. And this illustrates perfectly how these exact same rules apply to some of the most complex, mind-bending shapes in nature. Take a look at this 3D bicyclic terpene, isoborneol, converting into camphene. This is a very rigid structure. Yet, through a Wagner-Merowin rearrangement, it generates a carbocation, undergoes a 1-2 shift, and completely modifies its entire bicyclic skeleton. It literally unhooks a structural bridge and reconnects it somewhere else, all just to find a more peaceful, stable geometry. So, the big takeaway from this explainer is that the microscopic physical world is just incredibly dynamic, which leaves us with a pretty fascinating question to ponder. If molecules are constantly, spontaneously rewriting their own skeletons just to find physical and electronic peace, what other invisible, self-optimizing transformations are happening all around us every single second? Thank you so much for joining me on this deep dive into carbocation rearrangements. Keep wondering, keep learning, and I'll catch you next time.